Hello and welcome. Today we're going to be talking about momentum basics, finding total momentum. Well, how do you find total momentum? We know momentum is equal to mass times velocity, and we know the total of something is just all the individual components added together. So if we have a system with individual momentum, P1, P2, and P3, we might think that the total is just these three added together. So for example, excuse me. Let's say we have three bowling balls going in three different directions like this. And we find the mass and velocity for each one, and each one turns out to be exactly 8 kilogram meters per second. Alright, we'll call this object 1, object 2, and object 3. So to find the total momentum of the system, you might think, well, P1 is 8, P2 is 8, and P3 is 8. So I'm just going to add these three together. I get a total momentum equal to 24 kilogram meters per second. But actually, this is not true. This is not how this will work out at all. Because you know what? Momentum is not an ordinary scalar. It does not add with the ordinary laws of addition. We have to add it as a vector, because momentum is a vector. So the total momentum is the vector sum of all the individual momentums of the system. Momentum is a vector. Okay? In fact, in this example, if these three objects, these three bowling balls, are going exactly away from each other, in this situation, the total momentum is going to be 0 kilogram meters per second. Okay? So, just keep in mind that the total momentum is the sum of the vectors It's a vector sum of P1, P2, P3, P4, and however many objects you have. Each object has its own momentum, and you can just add them together as vectors. So we're going to be focusing on this today. Okay, let's go back to this example real quick. What's an intuitive way to tell that your momentum is going to be 0? Well, I'll tell you. Your total momentum is going to have the same direction as the velocity of the center of mass. So if you were to find the center of mass of these three bowling balls and pinpoint it right here, as these three bowling balls move away from the center, the overall center of mass of the system is still going to be right there at this point. That means the velocity of your center of mass is 0. It's not moving. So that means you have no momentum overall for the system. Each individual bowling ball has its own momentum, but the overall momentum would be 0. Okay? So I want you to think of P total as the momentum of the system as a whole. All right. What does this mean? Well, the mass of the system is going to be, well, the total mass of everything added together. And the velocity for your total momentum is going to be the velocity of your center of mass. So another way to write your total momentum, although we won't be using this today, is it's the total mass of your system times the velocity of the center of mass. And of course your velocity is a vector, your total momentum is a vector, and your mass here is a scalar. Alright, so let's go ahead and do an example. In this example, we're going to be finding the total momentum of a simple system that's going to consist of three birds. So I'm going to call this my 3 wet bird example. Okay, so in this example, we're going to have 2 ducks, top-down view, and these ducks, let's put some bills on here, and these ducks see a piece of bread, maybe right here, and they're both heading towards that bread. Okay? Each duck swims with a velocity, as you know, of 1.1 meters per second. And each of these ducks has the exact same mass of 4 kilograms. But there's also a goose. Something like that. All right, and this goose is also moving towards the bread. And it's bigger and meaner and faster. It's a 9 kilogram bird, and it's moving at 1.3 meters per second. So our job in this example is, of course, to find the total momentum. We're going to do this in 3 ways. First, we're going to find it in terms of unit vector form. Then we're going to find the magnitude of the total momentum, and then we're going to find the direction of the total momentum. Now, one thing we're not going to do is we're not going to simply multiply 4 times 1.1, 4 times 1.1, and 9 times 1.3 and just add them all together. That will not give us a meaningful number. Okay? We're looking for the total momentum. We have to add them as vectors. All right. So, let's go ahead and get started with this. First, I need to find the individual momentum of each duck, or of each waterfowl. So, first let's find the momentum. Let's see, let's call this duck 1, duck 2, and we'll just call this goose, G for goose. So let's find the momentum of duck 1. Well, it's going to have 2 components, right? So it's moving to the right, it's moving in the positive x direction, but it's not moving in the y direction. So it has no momentum in the y direction at all. So what we're going to do here is we're going to say the total momentum for duck 1 is the duck's mass times his speed in the x-hat direction, okay, plus 0 momentum in the y-hat direction. So this is his component of momentum in the x direction. This is his component of momentum in the y direction. And writing it out like this allows us to treat it as an algebraic expression. Okay? So M1 is 4 kilograms, V1 is 1.1. And I'm not going to even bother writing this out again, because I know it's just 0. So this turns out to be 4.40 kilogram meters per second in the x-hat direction. And that's the vector, that's the unit vector expression for duck 1's momentum. Okay, now let's do duck 2. Now duck 2 is going in the negative y direction only. He's not going in the x direction. He has no horizontal component of motion. He has only the y component of motion, and it's a negative component. So we'll write momentum of duck 2 is equal to, now it's going to be 0 in the x-hat direction. He has no momentum in x, plus, well, his mass times his velocity in the y-hat direction, because he only has a momentum in the y-hat direction. Now we've made a little mistake here. Look what we've done. Okay, that eraser's too big. So we've actually put a positive M1V1, but we know we know this has to be a negative. Because he's coming down, he's going the negative y-hat direction. So if m1 and v1 are both positive numbers, then we need a negative number overall for the y component. Now I'm just going to cross this out because we don't need it. It's just 0. Minus 4 times 1.1 in the y-hat direction, which is equal to minus 4.40 y-hat. So duct 2's overall momentum is negative 4.40 in the y-hat direction. Duct 1's overall momentum is 4.40 in the x-hat direction. They have the same magnitudes because they're the same size and they have the same overall speed, but they have totally different directions. So their momentums are not the same. Okay, now for this goose. Oops. All right, momentum for the goose. Okay, well, this goose is moving in the positive y direction. So again, 0x hat, and we'll go ahead and say positive, and this will be m goose times velocity of goose. I should say speed of goose since this is going to be a positive number in the y-hat direction. Of course, this is just 0. This is a nice example because each individual animal only has either an x-hat or a y-hat component to its momentum. All right, let's see. The mass of the goose was 9 kilograms. That's like an 18-pound bird. And its velocity is 1.3 meters per second. Geese are mean, by the way. Don't get too close. They're mean animals. All right, multiply these two together, and we get 11.7. And the units are, of course, kilograms, meters per second in the y-hat direction. This is a positive because the goose is moving in the positive y direction. Okay? So remember, this is the positive y direction, and this is the positive x direction. Now comes the easy part. We're going to be finding the total momentum of the system. Now what we're not going to be doing is we're not going to be simply adding 4.40 plus negative 4.40 plus 11.7, okay? That would be an overall momentum of 11.7 kilograms meters per second, and that is definitely not correct, okay? We have to add them as vectors. So we're going to add the vector momentum for duct 1 plus the vector momentum for duct 2 plus the vector momentum for goose. Okay? And the unit notation form is actually going to be really useful for this, and I'm going to show you how this works. So, let's see. For duct 1, what's the momentum? Well, it's going to be 4.40 kilograms meter per second in the x-hat direction. I'm going to leave off the unit for now. Okay? What about duct 2? It's going to be negative 4.40 kilograms meters per second in the y-hat direction, the negative y-hat direction. Now look, if we were just adding duct 1 and duct 2's momentum, the 4.40 and the 4.40 cannot cancel out. Look at this. You can't add these because they don't have like terms. The x-hat cannot add into a y-hat. Okay? Just like an x couldn't add into a y, we cannot combine these two terms. All right? And you'll see what I mean in a minute, in 1 minute. Okay, and the goose, well, the goose is going to have positive 11.7 kilogram meters per second in the y-hat direction. Now, what we're going to do now is we're going to actually combine, like terms. So the benefit of this unit vector hat notation, excuse me, is that we can actually just do this algebraically. We can actually get the answer just in one line, just using algebra. Watch this. So there's only one x term, so it's going to be 4.40, I should say x hat term, x hat, all right? And there's going to be two y hat terms, so I'm going to say plus negative 4.40, positive 11.7, okay? And all this in a bracket, y hat. You could use parentheses if you wanted to, just a style choice. All right, so look, I already know my overall component for my x hat. And let's just go ahead and work this out. Negative 4.40 plus positive 11.7 is going to be really close to 7.30 in the y hat direction. And that's it. If we want to find the total momentum in unit vector form, we've done it. Okay, so this is the first step. Now, I've also asked the question, well, what's the magnitude of this? So what is the, I guess we call it the strength of the momentum overall? It's not going to be 4.40 or 7.30, and it's not going to be these two numbers added together, okay? Remember, for any vector, the magnitude is going to be this. We use the absolute value sign to notate that it's a magnitude. It's going to be the square root of the x component squared plus the y component squared. All right? Now, where are my x and y components? Well, look, they're right here. Here's my total momentum for x, and here's my total momentum for y. Positive 7.30 for y, positive 4.40 for x. So 4.40 squared, I'll put a parentheses around this, plus 7.30 squared. Now notice, it doesn't really matter if these are positive or negative numbers. The magnitude does not care about the sign of each individual component. So I just worked this out, totally doing this in my head, and we get 8.52. Going to put the unit back in. It's going to be kilograms meters per second. And that's going to be the magnitude of my total momentum. Now, I shouldn't really say that magnitude is the strength of your momentum. That doesn't really make much sense, because there's already a physical component that has strength, and that's a force. So I don't want to confuse you guys. A magnitude is defined as the overall length of any vector. Okay? So if we were to draw this momentum vector, it would be 8.52 units long. All right, and last but not least, we're going to find the angle. Oh, well, we shouldn't just go ahead and get started. We should actually figure out which quadrant this is going to be in. So we have x and y, and the x component is positive, and the y component is positive. And you know what? This is going to give me a really strong indication that my overall momentum is going to be in the first quadrant. Okay? It has to be pointing in this quadrant. So the angle we're looking for is going to be this angle, the angle with respect to the positive x-axis. All right, and there's a formula for this. It's called the inverse tangent, and we've used this before. Okay, so it's going to be the inverse tangent of the y component of your vector divided by the x component of your vector. Our y component is going to be 7.30. Our x component is going to be 4.40. If you want the answer in radians, you better be in radian mode when you calculate this. We want to end degrees today, so make sure your calculator is in degree mode. Otherwise, you'll get a really bizarre answer. Oops, excuse me. I'll just go ahead and solve it. Again, totally doing this in my head. We get 58.9 degrees. This is your angle. So we know that any vector has two parts. It has a magnitude or length, and it has an angle or direction. All right. So the overall momentum of these three birds, it has a magnitude of 8.52 kilogram meters per second, and it has an angle of about 60 degrees from the positive x-axis. Let's actually go back for a second and see if that makes sense. All right, so I'm going to go all the way back to my diagram, and I'm going to sketch out, let's see, that should be about 60 degrees right there. I'm rounding up. You know what? That kind of makes sense, because my overall momentum for the system, well, this goose is adding a very large positive value in the y direction. So we know it should actually kind of cancel out the negative y component of momentum for this duck. So we would expect it to go in the positive y direction. And look, there's only one bird going in the x direction, either positive or negative. So we know the overall momentum has to be in the positive x direction. So this makes sense. The overall momentum of the system is going in this direction. And remember, if this is the center of mass, okay, well this isn't actually where the center of mass would be for these three ducks, or three animals, but this is the direction of motion of the center of mass, okay? Now the real center of mass, the way I've drawn it, would probably be about here. And as that goose moves up and these ducks move down, the center of mass would move in this direction, okay? All right, guys, hopefully this makes sense. Again, there's no hiding from it. Momentum is a vector, and you have to be able to deal with vectors to deal with momentum. There's no getting around it. All right, thank you and have a good night.